You're welcome to Random Numbers Lectures in Modeling Computer Simulation. Okay, the use of random numbers lies at the foundation of modeling and simulation. So when we need to model some computer applications such as simulation, games, graphics, etc., we often need these systems often need the ability to generate random numbers. But the quality of a random number generator that is employed is proportional to its period. In other words, it's proportional to how often the how is just like how the system is able to generate the number of random numbers it is able to generate before it starts repeating its pattern. Okay, now that's what determines the quality of a random number generator. Now in large scale simulations, different algorithms can be merged together. Okay, they can be put together, although these also have some drawbacks. Okay, but it may produce the best results. All right, now what is the definition? Random numbers are defined as numbers that show no consistent pattern with each number in series. Numbers that shows no consistent pattern. No consistent, this is very, very important. No consistent pattern with every other number in the series of numbers that are generated. Okay, they are defined as numbers that show no consistent pattern with each number in series, and at the same time not affected or predictable, okay, by the preceding number. Numbers that show no consistent pattern with each number in the series, and at the same time it is not affected by or predicted by the preceding number. Okay, so we cannot use the number that is following it to determine what the next number will be like. That's what we call random numbers. Okay, random number generation starts with an arbitrary number with specified number of digits. Okay, this first number is called the seed. How do we generate random numbers? We say that it starts with an arbitrary number. Call that number x. Now that number x can have specified number of digits. Let's say the number of digits is maybe 5. Okay, in other words, x can be equal to 18359, for instance. 18359. 18359. Okay, so this number now is called the seed, and this is our x equals to 18359. Now that same seed is multiplied by a constant c. Let our constant be 3. Let this be our constant. In other words, this will not change. Okay, by constants. Okay, this seed is multiplied by a constant number of the same number of digits. Okay, let's just say that maybe our constant number is going to be okay, let me just start afresh. Let x equals to 15934, and our constant is a number with the same number of digits. Let's say that this number of digits is 1, 2, 3, 4, 5. Okay, and the desired, when we multiply this, when we say that x times c, we'll now take whatever is equal to maybe y. So whatever, we can now take off what the number of digits we want at the end of the show. Okay, now let's assume the number is 15934. All right, 15934, and then I multiply it by 1, 2, 3, 4, 5. What do I have? I have 1967 05230. So I can decide to take two numbers. Okay, I can decide to take the last two numbers, and the last two number gives me 30. Now if I repeat the process, okay, it says the result now becomes the new seed. In other words, this whole thing becomes the new seed. Okay, it is again multiplied by the constant to generate a new product. Now whatever I have here, I can multiply it again by 1 2 3 4 5, and I'm going to get maybe what I have: 242 832 6064350. So if I take out the last two numbers again, I'm going to have 5. Now if I multiply what I have again times 1 2 3 4 5, you just notice that I'm going to have maybe 69 whatever at the end of it. So that gives me, when you continue the process, you have your random number. So this type of algorithm is called the congruential generator. Okay, that is how random numbers, one of the ways random numbers can be generated. The drawback of this is that it is obvious that generating a random number from a single seed works fine with most simulations that rely upon generating random events under the control of probabilities. Okay, it is obvious that generating this is going to work for this occasion, but however, although the sequence of number generated from a given seed is randomly distributed, one of the major drawbacks is that it is always the same series of numbers for the same seed. In other words, if you use the same seed, you are going to get the same series of number. Okay, now a computer poker game that simply used a given seed will always generate the same hands for each player, and in some occasions we may not want that. Okay, so this is one of the major drawbacks. So the question is now, how do we alter the seed? How do we alter the seed? The solution: what is needed is a large collection of potential seeds from which one can be more one can be more or less randomly chosen. So if we have in a pocket or in a container a lot of seed, we can randomly pick a seed from each and every one of them, and then apply the method on it, and then we'll start generating random numbers. But that's going to happen for each seed. Okay, so if there are not possible seed, the odds of ever getting the same series of numbers become diminishingly small. One way that we can do this is to have a way of taking the system's date or the system time and use it. It's in milliseconds. So for each iteration, you discover that the seed would have changed significantly. Now, another common technique is to use the interval between the user keystrokes. Now, by the time you press two things on your computer, the interval between them, which is usually a millisecond, is going to change. Although they are not perfect, yes, these techniques are quite adequate now for games, if you are programming games. Okay, the so-called true random number generator extract numbers from the physical phenomena such as radioactive source or even atmospheric noise as detected by a radio receiver. So the drawback of using the same seed all the while can be solved by either taking the interval between the user's keystrokes or the system clock time. Okay, the clock value in the system. All right, now we'll talk about pseudo random number generation. What we usually do in this instance is to fake, for instance, 10 pieces of numbers and 10 pieces of papers and number them. What you can usually do randomly when you are in you want people to, let's assume you are in a class and you want to decide who goes or who does something first. Now, for you to be able to pick, you may have to write the order, the number of paper, the number of sequences that you want, maybe 1 to 9, as you can see. Then fold them and put in a box. Then shake the box and have the first student to pick. Now, when the first student picks, whatever he picks becomes his position. So it's possible that out of 9 papers, out of 9 numbers that you wrote and folded into a box, and then when someone picks, it's possible out of those 9 that one person is going to pick number 8, another person number 7, and so on and so forth. And so by that way, you now know how randomly people will perform a task if it's maybe it's an allowed operation. So select the slip, then record the number that is on it, replace the number, and repeat this procedure over and over again. When you do that, you will continuously get random numbers. Now, if we want to simulate, in some simulation, we use random numbers to generate numbers between 0 and 1. Now, for example, if you need such numbers with 4 decimal digits, in this case now, then you can take 4 numbers at a time from the recorded sequence of random digits number, and then you place a decimal point in front of each of them. For instance, you want to pick numbers from 0 to 1, and you want it to have 4 digits. In other words, you're from 0.0001 to maybe 0.999. Okay, with this we have 1 and 10. We have 1 to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is a repetition of this, so we are going to put 0 here, for instance. Okay, now if you fold these numbers, somebody is going to pick maybe 4 at a go, and it's possible that he's going to pick maybe 2, 3, 4, 5. Now, if you want to put it, you write 0.2345, and then you fold these numbers back, and then you shake the box again and have the person pick 4 again. And that way, we are going to have something like what we have here. Okay, that's when you have a situation you want to simulate numbers from 0 to 1. Okay, now how does computer generate a sequence of random numbers? Now, one way is to perform what we've just done, what humans can do. Okay, sleep in a box experiment, and then store the recorded sequence in a computer backend store. Okay, this thing has a disadvantage. Now, when you do the first one, you store, do the second one, you store, and so on and so forth. Now, the disadvantage of this is that the advantage is based on the delays that's associated with reading data into memory from a tape drive. Okay, now the time it will take from getting the number and then saving it is one of the drawbacks of this approach. Now, experts have actually devised a mathematical process of generating digits that yield sequences, okay, satisfying many of the statistical properties of a truly random process. Now, for instance, long sequence of numbers generated using deterministic formula, you must note this, occur at nearly the same frequency. In other words, there is a model that is developed to be used to generate this. There is a model, and that model is a deterministic formula. Okay, what it means is that for every time that formula is going to work, okay, and because it is a formula, it's a model, it generates random number at the same frequency. Now, such a process is not really random. We call that process pseudo-random number generator. So that's pseudo-random number generator is actually a model that has been developed to be used in generating random number. But for a mere human being, is going to see it as a random number generator. It's like a random number generator. That's the word. That's the why this word is used. It is pseudo, is like a random number generator, pseudo random number generator. There are other ways of generating pseudo random numbers. Now, first is that computer simulation languages, and indeed some programming languages such as Python, have built in other words, this model has been developed and built into some programming languages. So in computer simulation, where this facility is not available in the language you are using, you will have to write your own pseudo random number generator. In other words, if you are developing an application and you suddenly discover that the facility, that pseudo random number generator, is not there, then you can as well write a system, write a formula, write a model that will be generating random number for you. Okay, that model must have to, one of the qualities is that it has to have a high entropy. Okay, high entropy. In other words, something is gonna make such to have high entropy. For instance, if you are using a seed, you must develop a system of constantly changing your seed. Okay, and that is where using the system clock comes into play, because at every interval you notice that the seed has changed. Okay, now the result of experiments such as the ones previously described above are published in books of statistical tables. So in performing hand simulation, it may be appropriate to use a published table of random numbers. That's when you are doing something on your own. But if you are actually developing a computer application, it may be better for you to either use the inbuilt pseudo random number generator that is available in most languages, or you develop a model that will generate pseudo random numbers for you. Okay, and that model is an equation that follows an iterative model, okay, to be able to output random numbers at every point in time. Now, the conventional six-sided unbiased die may also be used to generate a sequence of random digits in the set where each digit has a probability of 1 out of 6 occurrence. Now, if you have this and you want to select, you see that the probability of choosing 1 at random is actually going to be 1 over 6. Okay, so the entropy is, if you divide this now, the rate of change of this is going to be 1 over 6. So possibly going to be 0.1 something, 11 something. Okay, now let's look at using a random function in Python. Now, a Python random model provides various functions to generate random numbers and for us to simulate randomness. Okay, one of the most commonly used functions in the random model is the random itself, the random function itself. Okay, and this generates floating point numbers that are between 0.1 and 1.0. So in this session, we'll describe how to use Python's random function to simulate randomness and explore several other functions that are available in the random model. All right. Now, in order for us to simulate randomness with Python's model, we are first of all going to import that random model. Okay. So for us to simulate random numbers, we are first of all going to import it. So look at it. The way we import it is just to say import random. Now, when we now, and this random model has lots of methods inside of it. Now, just like I said previously, that the most commonly used is the random method itself, the random function. Okay, so inside of the random module you have a lot of random functions, or functions that you can use to generate random items. Let me use the word random items. Okay, now if we want to generate floating point number, we are going to import this random. We are going to import, first is to import this. Now is to instantiate this model. All right, now to say random dot this particular, in other words, out of this random model, call a function called random. Okay, and then you assign it to a variable. Now when you print this, you are going to get number from 0.0 to 0.1, or rather, sorry, to 1.0. Okay, that is what this does, generate floating point numbers. Now if we want to generate integers, now we are going to have the randint function, and it generates the integer n, which is going to be less than the first parameter a, and which is going to be greater than the first parameter a, but less than or equal to the second parameter b. In other words, if we have okay, let's assume we have randint 1 and 10. This is our a, this is our b. What it means is that the random number that we're going to generate is going to be between 1, 2, 3, 4, 5, 6, 7, 8, 9, okay, and 10 inclusive, because this thing is either greater than or equal to a, or less than or equal to b. Okay, look at the range here. All right, now another one is that we can still generate random numbers that are within a range. Now how are we going to do that? We are going to do that using the uniform function, and the uniform function takes two parameters also. Number one, two arguments. Number one is the initial, and that's the boundary. These arguments are actually the boundary. In other words, what you are going to generate is going to be within this range, from this point to this point. Okay, now if you now say 1.5 to 10.5, you are going to be generating floats, okay, random float numbers. Then you can still generate random number from a distribution, from a Gaussian distribution, by taking two parameters of interest. Okay, number one, the first parameter is going to be the mean mu, and the standard deviation represented by sigma. Now you use the Gauss function to do that. So the first parameter we are going to have there is going to represent the mean of the distribution, while the second parameter is going to represent the standard deviation, STD. So when you print this, you are going to get a random number from a Gaussian distribution. Now let's look at the overview of Python's pseudo-random number generators. Okay, the random model provides functions to generate a pseudo-random number, or to generate pseudo-random numbers. The numbers generated by this function are determined by a starting value known as the seed. So if the same seed is used, the sequence of numbers generated will be the same, allowing for reproducibility. We can find this applicable when we start doing machine learning or data science stuff. Okay, now seeding the random number generator. By default, the number generator is seeded with the current system time. That's what I've just explained previously. Okay, that the seed can be taken from the system time. All right, however, you can explicitly set the seed using the seed function for reproducibility. In other words, if you can change this seed by yourself, and if each and every one of us uses the seed of 42, it's possible that we're going to get the same random numbers. Okay, that is it. But if we don't set this, we can possibly use the system time to generate it. So we'll have functions that are there, which I've also explained. We have the random for returning random floating point numbers from between 0.0 to 1.0. You also have randint for returning integers, and uniform for returning floating point numbers, and then Gauss for returning random floating point numbers based on a Gaussian distribution with a mean mu and standard deviation represented by sigma. Now we have this function that you can as well apply, the choice, that returns a randomly selected element from a non-empty sequence, and shuffle, that shuffles the element of a sequence in place, and then sample, that takes the sequence and the k unique elements from the sequence. Okay. For us to understand pseudo-random number generators, there are three things we need to understand. Number one is its deterministic nature. Okay, it means that you can reproduce the sequence if you know the seed and the algorithm used. Now, in application, is suitable for applications that require random sampling simulation and simple games. And then in reproducibility, setting the seed will allow for reproducibility, which is crucial for debugging and testing. Thank you very much.